Hey everyone, in this video I'm going to show you that if you take a closed interval and you want to use calculus to find the absolute min and absolute max, or the locations of all of them, then there's a way you can do it, and it turns out that they're always located either at the endpoints or at a critical point. And the way we're going to get into that is first I'm going to show you something called Fermat's theorem, which says that if you are a local max or a local min, then you must be located at a critical point. And I've drawn a little diagram here to kind of illustrate how we're going to do this proof. So here's a picture of a local maximum. Remember, you're a local max or a local min. Local max in this case, if you can draw a small interval about your point where all the y values are actually less than the value f of c. And so I want to prove to you that the tangent line at this point, C, actually has zero slope. It's horizontal, just like I've drawn it. And having proven that to you, that'll actually show you the conclusion of Fermat's theorem. But let me back up a little bit and trace through the logic. So it's worth writing this down. So this is Fermat's theorem, and the precise statement of this is that, say you have f of c, and that's a local max or a local min, then one of two things has to happen. Well, first of all, you must be a critical point, which means that one of two things has to happen. Either your derivative is equal to 0, which is the case that I've drawn there, or your derivative does not exist, because that's what it means to be a critical point. So how do you prove something like this? How do you trace the logic? What you do is you say, suppose that I have a point C where f of c is either a local max or a local min. And I've drawn there the case of a local maximum. And then what you can do is you can say, let's assume that the derivative does exist. And then based on that assumption, let's prove that the derivative is equal to 0. Because then the only other case is that the derivative doesn't exist. That's handled for you. So to prove this theorem, it's enough to prove that if the derivative exists, then it's equal to 0. Because then the only other case that could happen is the derivative doesn't exist. So let's set about to do that. Let's prove that the derivative, if it exists, must be equal to 0. And the strategy for doing this is to say, well, if the derivative, that is to say the limit of difference quotients, exists, then it must be true that the right-hand limit, meaning the limit considering values that are bigger than c only, must be equal to the left-hand limit. That's the limit that you get considering values less than c only. Those two things must be equal to each other, and they must be equal to the derivative. That's just one of these facts about limits. You take a limit, then the y values have to approach the same value so long as the x values are close to c. Doesn't matter whether they're close on the right or close on the left. On the other hand, if you take x values that are close to c on the right-hand side, look at the slopes of those secant lines. So the slopes of those secant lines are the values of the difference quotients. The slopes of the secant line here, they're all negative, or they're all less than or equal to 0. So when I take that limit from the right-hand side, the answer that I get has to be less than or equal to 0. It can't be positive because it's a limit of things that are negative. Same way over here, now the slopes of the secant lines, the values of that difference quotient, they're all positive, sloping upward. So the limit must be bigger than or equal to 0 because it's a limit of things that are positive. So you have a limit that on the one hand is non-negative, and on the other hand is non-positive. The only option is that that limit must be 0. It's like saying the derivative is equal to 0. So let me write that out a little bit more explicitly. If I can say that the f prime of c, that's the limit as h goes to 0, f of c plus h minus f of c all over h, that's equal, first of all, to the limit of the right-hand limit that's going to be c plus h minus f of c, just writing it down again, over h. So I'm calculating this limit by going from the right. And when I do that, when I look at this difference quotient, I can say, okay, so what is f of c? So if f of c was a maximum, then it has to be the biggest point. It has to be bigger than this point, which means that this difference is less than 0. And h, coming from the right, must be positive, so negative over positive means that this difference quotient was negative, and so the limit of a sequence of negative numbers surely has to be less than or equal to 0. And you could have a sequence of negative numbers increasing up to 0, but never getting bigger than 0. And on the other hand, I could look at the limit as h goes to 0 from the left. It's the same difference quotient. But this time, as you can see in the picture, well, you've got something that's negative up on top because this is the maximum. So you're subtracting something, bigger than or equal. Something that's negative, or at least non-positive, divided by something that's negative because I'm going from the left. And that gives me a difference quotient that's definitely bigger than or equal to 0. You take that limit, it must still be bigger than or equal to 0. So that you put that together and you can conclude that f prime at the point C must be bigger than or equal to 0, and f prime of C must be less than or equal to 0. Well, the only way that can happen is if it's equal to 0. And the proof in pictures is you just look at those secant lines. The derivative is the limit of slopes of secant lines. You're looking at, on the one hand, a limit of negative slopes or non-positive slopes. On the other hand, you're looking at a limit of positive or at least non-negative slopes. And that gives you that conclusion. So that's Fermat's theorem. And then the way you go from this to what I said at the beginning of the video, that is this statement about where can extreme values be located. So two things. First, I'll remark that if that were a minimum instead of a maximum, this argument would still be completely correct. It's just that going from the left would be positive and going from the right would be negative, and you'd still make that conclusion. So this is completely general. You can do this the very same way if it's a minimum. So this works no matter whether it was a max or a min. So now if you're in the situation where you've got just some function on a closed interval, we'll draw one here, interval from A to B. Closed means that the interval contains its endpoints. And maybe the function looks like that. And so the extreme value theorem, if you like, says that if you want to search for the absolute max and the absolute min of some continuous function on the closed interval, only two things can happen. So either that maximum occurs at an endpoint, like it does here, or the maximum or minimum occurs at a critical point, like it does here. That's called the extreme value theorem. If you want to find absolute max and min, you need only check the endpoints first and check for critical points. How do you prove that? Well, you just check and look and say, are the absolute max and min occurring at the endpoints? If yes, then you're finished and the theorem is correct. If no, then the absolute max and min must also be a local max and min, because if you're not at the endpoint, then you'll be able to find a little interval around it where it's the smallest thing. And then you can apply Fermat's theorem and say, if you're not at the endpoint, then your absolute max or min must have been at a critical point. And so that just completes for you this either-or situation where absolute max or min must be endpoint or a critical